good day, everyone. And once again, we are back together. All right, so today we'll be looking at just quickly looking at the projectile motion, particularly that graph scenario, because some of you have been asking me for those interpretation of graphs. Right, so I thought we'd look at the bouncing ball scenario because I think that would make the most interesting of topics to just cover quickly. Right, so they tell us that a 50-gram ball is dropped from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02. Okay, ignore all effects of friction. Right, now we also need we always need to be mindful when we're looking at the bouncing ball scenario. Now, if you think about it, if you interpret this graph, so it means this ball must have started from 0, then the velocity increased, in this case, in the positive direction. Now, given that it was dropped, so it must mean that we've taken downwards as positive. All right, I hope that makes sense to you, because remember, as it goes down, the velocity increases, right? And in this case, when you interpret the graph, look at that. The velocity becomes more and more positive, obviously, as the ball bounces. Now, what happens? Then it reaches a maximum velocity, in this case of 3.92. This is when it gets to the ground, right? Just before it hits the ground. And then it collides with the ground for that period of time between 0.4 and 0.42. So again, it means it was in contact with the ground for 0.02 seconds, as they did indicate there, right? So it was in contact with the ground for exactly 0.02 seconds and then started moving upwards. How do you know that? Then the velocity started becoming negative, right? And then remember, as it goes up, the velocity is decreasing, but it's decreasing in the negative direction. So you see there, it's negative until it gets to 0. So that would be at maximum height. So this one shows us at maximum height. We just need to keep that in mind. Okay, this is after the bounce, right? And then, so that means this is when it got to the ground. Okay, this is when it left the ground. Okay, and this is when it got to maximum height, and again it reaches the ground for the second time. All right, so I hope that kind of makes sense to you. Okay, so okay, actually I should have written the other ground there. Okay, so let's say ground 1. Okay, so this is ground 2. Okay, right, so let's have a look at it quickly. So they say to us, define projectile. I'm sure by now, guys, you are able to actually sing these. Okay, in this case, obviously we're looking at the motion of an object, okay, due to gravitational force only. Okay, right, so I won't really focus much on definitions. So write down the magnitude of the velocity with which the ball leaves the ground after bouncing, right? Okay, so let me just remove that. Okay, so do you see they said to you write down? Okay, so in this case, it means the answer is right in front of us. So what is that? The velocity when it leaves the ground immediately after bouncing, that would be that velocity, negative 3.43. Okay, so that velocity is 3.43 meters per second. But remember, it was going upwards. Okay, right. And then they say to us, draw a labeled free body diagram of all forces acting on the ball at 0.77 seconds. Right, so this is when we reach the maximum height. So please remember, guys, when we get to maximum height, it doesn't matter where the motion of the ball is. What are the forces that are acting? It's always going to be just the one force, and that is gravitational force, right? So it doesn't matter whether they say at maximum height. The only time where there's more than one force is when it gets in contact with the ground, right? So in this case, for 3.3, we're going to have just the one, okay? So that's going to be the force of gravity, or you can say the weight of the object. All right, so that is by definition what we mean when we talk about projectile motion, right? They say use the information on the graph, and calculate the acceleration of the ball. Now, we know that acceleration is due to gravity, right? But they want us to calculate it using the information on the graph. So what are we going to do? Right? So it means that we need to calculate the gradient. Remember that in a velocity time graph, acceleration is indicated by that gradient. Okay, so you can actually use, let's say, the origin as well as that point there. Okay, so my gradient, if you don't mind, I'm just going to do it over here. That's going to be change in velocity divided by change in time. Okay, change in y over change in x. So that's 3.92 minus 0. Okay, but when the velocity was 3.92, the time was 0.4. So that would be 0.4 minus 0. Okay, so if you calculate that, so you've got 3.92, okay, minus, well, let me not even say minus 0. I mean, you know that's going to be 3.92, right? 0.4. If you don't know that, meters per second squared. So there we have it. It's positive 9.8 meters per second squared. Okay, so I hope that you were able to see that for question 3.4.1. Okay, so 3.4.2, they say to us, calculate the height from which the ball was dropped. If you don't mind, so that it becomes easier for us to look at, I'm going to do the question just here. Right, now please keep in mind, when we calculate the height or displacement in a velocity time graph, what you do is you calculate, you look at, in this case, the area underneath the graph. Now, if you look at this, right, where is it that we started from the top of the building? Okay, so that was at time 0, right? And then what happened? We dropped it down, isn't it? So that would be when it arrives at the ground. So this is from the top, obviously. This is when we arrive at the ground. So I can take the area underneath that portion there, right? So I would say, well, what is my area? So the area underneath the graph, that's a triangle. That would be half base times the perpendicular height. Okay, so that would be half. Our base is 0.4. Okay, and our height is 3.92. Okay, so we're going to say, right, that's 0.5 times 0.4 times 3.92. Okay, and I get a height of 0.784 meters, right? So that would be 0.784. So 784 meters. Of course, I've shown the calculation there. All right, so the last portion of this segment, okay, we're going to look, there's another subsequent question. They say to us, on the same set of axes, on the set of axes rather, draw a position time graph for the motion of the ball. They say from 0 to 1.12, okay, In this case, they said use the ground as zero reference, indicate the height from which the ball was dropped and all relevant time values, okay, on t-axis. Okay, right, so we're now considering a position time graph. All right, so for the purpose of this graph, if you don't mind, I'm going to take upwards as positive, because then it becomes easier for us to draw this graph, right? So that would be the position in meters, as well as time in seconds, right? So in this case, I'm going to have the position of the ball. Remember, it started 0.78 meters, 0.784. Okay, so that's 0.784 meters, and then fell to the ground. Okay, and then for that little bit of time there, spent some time on the ground, and then it went up. Okay, and I am assuming that, of course, you can see that area of that triangle is smaller there, so which means it did not get to the same height. Okay, so and then it came back to the ground. Okay, so that's what we saw there. So it went up, got to maximum height, and then we said it comes back to the ground. So that is what our graph would look like. Nothing wrong if you considered, obviously, if you consider down as positive, your graph would just be a reflection about the time axis, right? So it would look something like this. Okay, now let's put all the relevant time values. So it arrived on the ground at 0.4, left the ground at 0.42, okay, got to that maximum height at 0.77, and then got to the ground 1.12. And remember, this is time in seconds. And that is how your position time graph would somewhat look like. Okay, right. Now, they say to us, give one term for the rate of change of momentum. Okay, please remember, when we talk about the rate of change of momentum, in this case, that's the net force. Okay, now if you think about the momentum, the impulse momentum equation, we've got change in momentum, or rather force multiplied by time is change in momentum. So once you divide by time on both sides, then you've got, actually this is net force, sorry. So net force is the rate. Remember, when we say rate, it's division by time, okay? And so that would be the net force, okay? Right, yeah, so that's the net force. Okay, right, now let's consider the next one. They say calculate the magnitude of the force exerted by the floor on the ball for the time of contact. Now we're going to use exactly that. So we're looking for the force, right, multiplied by the change in time. Okay, so that's 3.7. So multiplied by the change in time, which is equal to change in momentum, right? So now we're looking for the net force. What is our change in time? Now remember, the time of contact, in this case, it's between 0.4 and 0.42, which was 0.02, the time of contact with the ground. Okay, and in this case, now remember, change in momentum, that would be mass times the change in velocity, final velocity minus initial velocity. Now you need to keep in mind, when we say final velocity, this is the velocity after, when it leaves the ground. And when we say initial velocity, this is the velocity before it touches the ground, right? So the mass was 50 grams, I believe, right? So please note, you need to convert that to kilograms. So we say 50 divided by 1,000, okay, that would be 0.05, our final velocity, this is now after the bounce, right? In this case was negative 3.43, and before it was 3.92, right? So that's negative 3.43, and you need to consider direction here, right? Minus, now remember there's a minus sign here, minus a positive 3.92 rather. So in this case you've got that there, right? So that's F net times 0.02. Okay, so divide obviously both sides by 0.02. Okay, and so I've got 0.05 into negative 3.43 minus 3.92. Okay, and we've got that there divided by 0.02, and we've got negative 18.38. Okay, right, remember we are talking force in this case, so that would be in newtons. All right, so that would be the magnitude of the force. And of course, why are we getting it as a negative answer, right? Obviously because the force was acting upwards when it collides with the ball, right? Okay. Yeah, they did say the magnitude, so we didn't need to specify direction. Right, now they say to us, if a softer ball is used and the time of contact with the floor is increased while the change in momentum remains constant, how will this influence the force on the ball, right? They say to us, write only increase, decrease, or remain the same, or explain the answer. Okay, now they have somewhat explained it to you, right? Now, if we use a softer ball, what will happen? It means that the time of contact with the ground, will increase, right? Now, I'm going to show you just now using this equation. So the time of contact with the floor will increase, and they did say whilst, momentum remains constant, right? Right. So how will this affect the force? The force would decrease. I'm going to show you just now. Okay, so that was 3.8, right? 3.8. So if you look at that, F net is change in momentum divided by change in time. Now, what happens when you use a softer ball? It means that the time of contact would decrease. Can you see that? Time is in the denominator, right? So in this case, because they are inversely proportional to each other, it means that the net force would decrease. So your first answer there is that your force would decrease. Okay, right. So how do we explain it? A softer ball would increase contact time with the ground, okay, with the ground, but in this case, because change in momentum remains constant, why is that? Okay, so change in momentum remains constant, therefore the net force will decrease. Okay, since the net force is inversely proportional to the time of contact. Okay, right. So that is essentially how we'll answer this question. I hope that you enjoyed it, ladies and gents, and I'll see you guys again next time. From me, your favorite uncle, Sharp Sharp.